in Glassbox interpretable machine learning, especially using neural nets. And most of this does not connect yet with computer vision, but this is a workshop. Hopefully we'll be able to figure out how to do that. And I'll talk a little bit about that at the very end. Just so you know, half of what I'm going to present is from this paper we did at NeurIPS last year called Neural Additive Models. And this is joint work with Jeff Hinton, some people at Toronto and Google, and some other people at Microsoft. So let me jump right in. Give you an introduction to these generalized additive models. Before I do that, you might have heard that there's this accuracy and intelligibility trade-off. The most accurate things like deep neural nets are, black boxes, and the things that are more interpretable, like logistic regression, are not very accurate. For tabular data, this is just no longer true. It turns out that we now have a method, these explainable boosting machines, which is just as accurate on tabular data as things like deep neural nets, boosted trees, and random forests, but it's even more interpretable than Glassbox methods like linear and logistic regression. So I'm going to tell you a bit about those things, how we train these generalized additive models. Just to give you some evidence for this, just look at the left column and the right column. So these are Glassbox EBMs on the left. This is classification. Here's 10 data sets. Average accuracy is at the bottom. It's 0.866. And on the right, we've got some full complexity models like random forests and gradient boosted trees that have been optimized for depth. And notice that the average accuracy of the best of those is also 0.866 on these data sets. So here we've got sort of parity between the accuracy of a Glassbox method and black box methods. And later I'll show you some results with deep neural nets. Also, there's been some work from Cynthia Rudin's team over at Duke, and they've done some comparisons using our method and other methods. And they also find that we seem to be, these EBMs, the most accurate Glassbox method, and that the accuracy of this method is comparable to the best black box methods, things such as XGBoost. Okay, let me tell you what these generalized additive models are. On the left here, we have linear logistic regression. These are the simplest additive models. They're very interpretable because they're very straightforward. They're not as accurate as we would like because they can't really model nonlinearities. And sometimes, by the way, these things struggle to fit the data so much that they actually get the sign of some of the terms wrong because they're trading off errors of poor fit on some terms with error of poor fit on other terms, and they actually get the signs wrong. On the far right now, we've got black box machine learning. Think of this as a deep neural net or boosted trees. Not very interpretable, that's why we call them black boxes, but they can, of course, be very, very accurate, and that's because they easily model nonlinearities. They are a little more likely because they're so complex to learn spurious effects, and the previous talk was really interesting because maybe we can reduce some of these spurious effects by taking some causal learning into account. In the middle, we have generalized additive models, of which EBMs, explainable boosting machines, is just one example. These are more interpretable than linear logistic regression because they actually give you these sort of graphs. And experts find these graphs, which like have a low spot and then rapid rise and then a flat spot. They actually find these more informative and interpretable than, say, a straight line would be in a linear model. But they can still be very accurate because they can easily model these nonlinearities. Importantly, because these are constrained models, they're more likely to show sort of significant effects. And in fact, they often detect things that look like they're causally true, but these are not causal models. These are just standard supervised learning models. And by the way, these things were invented by Trevor Hastie and Rob Tibshirani, at Stanford in the late 80s. So this is Trevor's thesis. These things have been around for 30, 40 years. And our contribution is going to be to have new algorithms for training these things, put them on full sort of machine learning steroids, and then build an ecosystem around them and get them basically performing as well as black box methods and also give them some advantages. So let me tell you briefly what these are. A linear model, of course, is an intercept plus a weight times a feature plus a weight times a feature. And you just sort of interpret this sort of linear model usually by just looking at the coefficients. You don't even typically plot the graph. On the right, we've got a black box method. It's just some arbitrarily complex function of all the available features. In the middle, we have what's known as an additive model. So it's a function of a feature plus another function of another feature. Every feature has a function associated with it. And then because these are functions of single features or maybe pairwise interactions, we can plot these functions and we can understand what the model has learned. So we can make this a little more complicated. This is the sum of all functions of individual features. Here's the sum of functions of pairs of features. This can now do pairwise interactions. We can go all the way to three-way interactions if we want, but usually we try to stick with main effects and a small number of the most important pairwise interactions, because this remains very interpretable. And then the surprise is that if you do this really carefully, if you do it very, very well, you can get the accuracy of this model class on most tabular data sets to be equal to the accuracy of black box learning on those same data sets. Let me show you briefly how these EBMs are trained, and then we're going to jump to neural nets. Okay, so what we do is we go to feature one. In the first iteration, we grow a small tree on feature one. Update the residual, go to feature two, grow a small tree that can only use feature two, go to feature three, small tree that can only use feature three. So now we've grown a tree for each of the features in round robin fashion, and each of these trees can only use the feature that they're allowed to use. Second iteration, we add a second tree for feature one, a second tree for feature two. We keep updating the residual. So this is a standard boosting algorithm. We do many, many iterations, as many as 10,000 iterations, and we use early stopping on a validation set to tell us when to stop. In the end, we have a column of perhaps as many as 10,000 trees, all of which were trained on feature one, another 10,000 trees all trained on feature two. And what we can do is we can take all the trees trained on feature one, we can ask them what they predict combined together, and we can draw a graph. So what do you predict at age 18? What do you predict at age 19? What do you predict at age 20? We draw the graph, and then we can throw those trees away because the graph now perfectly captures what they would predict. We do that for each column, and we now have a graph that represents what this model has learned about all of the features, and we're able to throw away all of the trees. In the end, the graphs are the model. There's limitations, though, of these tree-based generalized additive models. Although these things have been sort of state-of-the-art in Glassbox learning for about 10 years, let's face it, half of the machine learning community uses neural nets. They don't use boosted trees or scikit-learn. And algorithms based on boosted trees don't scale as well as deep nets do because they're typically not trained on GPUs. GANs that are trained on boosted trees are also not differentiable, and that really reduces their flexibility. I'll show you an example of this later. Models trained with neural nets are also just much more modular and flexible. And it's hard to get some things like multicast learning even to work well with boosted trees, whereas it's very easy to make this work with neural nets. I'll show you an example of that as well. So let me now tell you about these neural additive models. So how do we fit GANs, generalized additive models, which have to be functions of individual features that then get added together? How do we do this with neural nets? Well, it's actually pretty straightforward to create an architecture to do this. So here's feature one, and it goes into a deep subnet, but this deep subnet is only allowed to see feature one. So it is constrained to learn a function of feature one. In parallel, feature two is going into its own deep subnet, and this subnet is learning a function of feature two. And then these things get added at the end. So this is an additive model. It's an additive model of functions of individual features, but we've now used deep subnets to learn these functions. And if we're doing regression, in fact, we don't even need a sigmoid, we do a summation here. And if we're doing classification, typically we'll go through a sigmoid or something like that at the output of the network. And then all of these things are learned in parallel just through gradient descent. In fact, there's really nothing too special you have to do once you create the architecture to do gradient descent. And this can be trained at scale on GPUs using pretty standard software. And then here's the really cool thing. Remember with the trees, we threw away all the trees and replaced them with graphs. Well, this function, which is just a function of feature one, can also be replaced with a graph once we figured out what it should be by training the network. So we just sort of scan through all the input values, all the output values coming from this last node, and then we replace that with a graph. We do that for every one of the subnets. And in the end, we actually can, if we want, throw the neural net away. And what we have is a bunch of graphs that represent the function. So this is an alternate way of training these generalized additive models, but now using deep neural nets as our learning method. There is a problem, though, with doing this. And the problem is that EBMs, the boosted tree versions, show that jumps are very important in graphs. This is a pneumonia risk as a function of age. Notice there's a jump in risk at retirement age, jump in risk at 85, drop in risk at 100. These jumps in risk are actually very important for helping us understand what the model has learned, understand the data, and also for the accuracy of the model. This is your chance of dying in the ICU as a function of how well you're breathing, and this drop in risk that's happening right here, the sharp drop and then re-rise, is very, very important to the model. In this case, it's caused by missing values, and the model would not be accurate if it could not learn this jump. This is a lending data set, and it turns out this rapid rise at 4,000 is a very important part of the model being accurate and also of us understanding the model. This is the most interesting one, perhaps. This is from Wikipedia, and this is the amount of time since a person has registered to be an editor at Wikipedia. And you can see that people who have been editing for a very short period of time are considered very high risk. This is on a log scale on the vertical axis, where people who have been editing for a short period of time for a long period of time are considered very low risk. And these jumps all happen at round number intervals, which suggests that they're causally true. And in fact, we can identify the causal mechanism for each of these jumps. The most interesting one is this 1 month jump. And it turns out this is so important that leading up to the last presidential election in the United States, it turned out that Wikipedia decided you were only allowed to edit sensitive pages that corresponded to the election if you had been editing more than a month. And that's because people who had been editing less than a month were much more likely to be trying to spread false information, and they didn't want that happening prior to the election. So even companies like Wikipedia can use these interpretable models to make important policy decisions. Okay, so now all of this shows you that learning these jumps, these nonlinearities, is important. But neural nets are not very good at doing this. So what we've done is we've created a new kind of hidden unit, an XU, and it's just like the standard one where this would be a weight times X minus B, but instead we exponentiate the weight. And that means that small differences in the weight can now lead to very large differences in the activity of that hidden unit. So here's some completely random data, which should be hard to fit. And on the left, we have just a standard hidden unit. And you can see it's not really capable of overfitting massively and hitting these points. On the right, though, if we throw in an XU, you can see just like a polynomial of very high degree, we're able to overfit massively and hit all these points. And we want the model to be able to do this. Here's the interesting thing. Now, overfitting is less of an issue in generalized additive models, but we still want to further reduce overfitting. So we apply dropout, we do weight decay, we cap the ReLU activation so they can't go to infinity. We bag the NAM model, say 25 to 100 times to form an ensemble. We do all sorts of things to do variance reduction after we have learned the model that can learn these jumps. And now if it learns the jumps consistently, like at age 85, there's always a jump, that jump will survive all of these different approaches of doing regularization. But we want to make sure that the model can learn those jumps in the first place. Let me show you some empirical results. Okay, on the left, we've got classification data sets, 3 of them, and on the right, we have 2 regression data sets. And this is AUC, so up is good on the classification data sets and squared error on the regression data sets, so down is good. So linear regression, logistic regression, decision trees, they do okay, but they're not really high flyers on either of these kinds of data sets. Now, gradient boosted trees that are full depth, deep neural nets that have been well optimized, these actually do very, very well on these data sets, as you would expect. So they're sort of setting the goal, the target accuracy we want to achieve. The amazing thing is in the middle, we have these neural additive models trained with the method I just described. And for comparison, these EBMs. And first, you'll notice that NAMs and EBMs are very comparable in accuracy. Sometimes EBMs win, sometimes NAMs win. It's basically a tie between these things. And then also, if you look carefully, you'll find that often these NAMs are doing as well as the full complexity models, gradient boosted trees and deep neural nets. That's great. The one exception we see to this is we do find that deep neural nets are particularly good at regression, and they do slightly outperform the best interpretable models that we're able to train on this data set. So regression is the one setting where the deep neural nets sometimes pull ahead by a little bit, not by a lot, over the NAMs. So there's little loss in accuracy overall for these NAMs compared to deep neural nets, as long as we're talking about tabular data. So let me just show you some things that these models have learned. So this is a ICU mortality data. You're in the ICU, we're trying to predict the chance that you might live or die. These are the graphs that were learned with the NAM using that, or subnets that I was telling you about before. Let me just show you a few of them. This is risk as a function of age. And notice that risk kind of roughly monotonically increases. There are some interesting jumps that happen at clinically meaningful ages. Notice it also says that people who are extraordinarily young, which is rare for them to be in the ICU, are at actually elevated risk. So this is an interesting model, and it confirms other things we know about this data set. This is risk as a function of the Glasgow coma scale. Turns out people at 1 on the scale are in full deep coma. People at 5 are just ambulatory, normal, like you and me. And the model has learned a sort of monotone decreasing risk as you're in less and less severe coma. And there's nothing that's biasing the model to have to be a monotone decreasing function. It has just learned this from the data. This is a renal failure, and here 4 means you're in severe renal failures, 0 means normal, and here that has learned a monotone increasing function. So this is good to know. And then the last thing I want to show you is systolic blood pressure. This is the higher of your 2 blood pressures, and this has learned a really nice non-monotonic function here. So it's learned that normal is in the middle, that sort of blood pressure between, let's say, 110, 120. Risk is going up as your blood pressure gets higher. Risk also goes up as your blood pressure becomes abnormally low. And there's these interesting bumps, which we really wanted to see. These are treatment effects. It turns out, once you see, notice that just beyond 200, your risk actually goes down. It's not the case that having extraordinarily high blood pressure is good for you. What happens is you hit 200 and the doctor's like, your blood pressure is over 200. We really have to do something about this. And they give you very aggressive treatment because you've crossed this round number threshold. And you just heard that your blood pressure is over 200. You know that's a crazy high number. You're very likely to do what the doctors tell you to do. So in fact, people at 205 are lower risk than people say at 195. And that's because they've passed this magic threshold of 200 where they're suddenly getting very aggressive treatment and they're paying attention to it. It's an additive model. You put the patient in, every one of these graphs predicts an additive score, and then you add all those scores together. And because these components are somewhat independent, we can actually reason about how each of these terms, such as blood pressure or renal failure, contributes to your risk. Let me show you briefly how we benefit from the differentiability of these models. So this is a very complex architecture created by Ben Lengerich, one of the co-authors. And I'm just going to briefly tell you how these things work. We're learning a single task NAM at the top, and the single task NAM gets to see the meds you were taking before you got to the hospital. It seems that it gets to see your illnesses and some demographic backgrounds, things like your age and gender. It's also getting to see the results of lab tests when you're first admitted to the hospital. And the single task model is trying to predict your mortality risk if you were not treated, because there's no treatments getting to this model. And that's trained exactly the way we talked about before. This is a multitask NAM, which we haven't talked about yet. It gets to see everything the single task NAM sees, but it also gets to see the medications and treatments that you receive once you're in the hospital. And this multitask NAM is trying to do something very hard. It's trying to predict for every possible treatment a patient could receive, how much does that treatment lower the risk of the patient? And then notice that these things get summed together. So we have the risk if you were untreated from the top single task model. And then at the bottom, we have the multitask risk for all the possible treatments. And then this little node here basically says it's only going to lower your risk if you receive that treatment. Otherwise, it doesn't affect you. And in the end, all we actually get to see as labels is the final mortality risk of the patient, whether they live or die. So this is an amazing model. All it is seeing is input features and mortality risk. And it is trying to disentangle your untreated risk from your treated risk and the benefit of each of the treatments. It's really an amazing thing. And you wouldn't be able to do this without this kind of a NAM architecture. Let me just briefly show you some results. So this is the benefit of a treatment as a function of your age in years. And the 3 treatments are anticoagulants, NSAIDs, and glucocorticoids. And by the way, this is COVID-19. We've been doing a lot of work on COVID. So, and you can see that as the patient gets older, their expected benefit from an anticoagulant, from an NSAID, which is like aspirin, or especially from glucocorticoids, decreases. That they're less likely to respond to these treatments, which is unfortunate. And it's why mortality risk is particularly high for elderly patients. This is the same kind of benefit in treatment of for these 3 different treatments, but this is for your NLR ratio, which is one of the lab tests. And notice that it has learned that if your NLR ratio is very low, anticoagulants are not likely are likely to help you a lot, but if your NLR ratio is high, they're not likely to help you. It's even worse for NSAIDs. They're going to help you most if your NLR ratio is not bad, but if you have high NLR, they're not going to help you that much. Interestingly, we have a different story when it comes to the glucocorticoids. Here, the higher your NLR ratio, the more they're likely to help you. And this is really an important kind of finding because it basically helps us decide what kind of treatments. If you have low NLR ratio, we definitely want to throw something like an NSAID at you and maybe an anticoagulant. But if you have high NLR ratio, then it turns out because these other treatments are less effective, we also want to throw a glucocorticoid steroid at you because it's most likely to help you. Okay, let me tell you about multitask learning because we just used it in that previous architecture. So here's a single task NAM. This is a picture I showed you before, right? Subnets, they're being trained on individual features, summation at the end. Here's a multitask NAM. We've got 3 output tasks on this, and notice that the summation for each of these tasks goes over the same graph. So the graph that's learned from feature X1 is being used by each of the 3 tasks, and each of the tasks is able to put its own weight on this subnet. So it can use a strong weight to it, a weak weight to it. It could even negate the graph, like turn it upside down with a negative weight, though that's unlikely to happen. It turns out this works pretty well, but there are ways to make this better. This sort of forces sharing. You're only learning one graph that all of the tasks have to share or not share. So that's a little too strong. So what we actually like to do is use multiple subnets per feature. So here we're learning 3 different subnets for feature 1, 3 more subnets for feature 2. And you'll notice that each task gets to choose its own weights to these different subnets. And this means that the task can decide task 1 and task 2 maybe really like the same graphs for feature X1, but they like somewhat different graphs for feature X2. And we can even look at these weights and sort of figure out how the tasks are clustered by how much they like to use the same graph. Importantly, even though we end up with multiple graphs on the inside of the network, once you take these weights into account, that just becomes a weighted average over graphs. And it turns out for each task, we're still able to plot the single graph that that task is using. If we want, we can look at the basis functions of the graphs that were used weighted to create that average graph, but we don't even have to do that if we don't want. We can just look at the final graph that each task is using. And this has the usual multitask bias towards sharing these graphs. Let me just show you an example of this in action. This is the COMPASS data set where we're predicting recidivism for people who have hit the criminal justice system. Normally, this is trained with single task learning. So basically, you've got about 75% men and 25% women in the data set, and you typically just train one model for everybody. And if you look at the results at the top, you'll see that when you train a combined model, single task fashion, you do reasonably well. But if we do a multitask NAM that's looking at a separate model for men and for women, it actually does a little bit better. And in particular, it does better for men and women. And let me just show you 2 examples. Charge degree, this is whether you've committed a felony, that's a 1 or not. And the single task model has learned that, committing a felony makes you more likely to commit another crime. But notice on the right that the multitask net has figured out that for women, in fact, women don't commit as many felonies, but when they do commit a felony, they're even more likely to commit another crime. And if they haven't committed a felony, they're actually less likely to commit another crime. At the bottom, we have risk as a function of race, and we have the usual thing that unfortunately we often see, which is that African Americans are predicted as highest risk, whites as less risk, in this case, Hispanic even lower risk. That's the single task model trained on everyone. But if we're now doing a model that is able to see women, then that model learns something quite different from men and women. What the model ends up learning is that women actually are highest risk if they're white, and they're lower risk if they're African American, which is quite a different story for men. Okay, I haven't talked, very much about vision, and that's because pixels are not tabular. If I tell you someone's age or their income, you know what that means. If I tell you pixel 463's red channel has a value of 12, You don't really know what that means without me telling you more about it. So, what are we going to do? Well, it turns out in some domains like radiation oncology, which I have a collaboration on, they actually do like tabular features. So the original detection and diagnosis is done by a radiologist or a deep neural net looking at the images. But once they have the image, they then do extra work to convert it into tabular features, things like the size of the tumor, the density of the tumor, the edges of the tumor, things like that. And they like to do that because they typically like to classify tumor into stages. That's easier to done with these tabular features. They might want to predict survival or decide what treatment and dose to use. And these things are all things that they prefer to do using the tabular features. So we find that the NAMs are really good, even in this image-based domain, because they like tabular features in this domain and they know how to compute them. And the NAMs are even better, and that's because they're good for multitask learning and survival analysis. So you might have heard of Lyman Schaap. I mean, they're explaining black box models. How are they doing that for images? Well, typically what they're doing is they're converting the images into superpixels, foreground and background, or object parts. And then effectively, they're creating things that are like tabular features out of the images. And if you're going to do that and create these tabular features, we can also use these NAM models to do that as well. This is taken from Marco Ribero's line work. Now, we could do some crazy things. We could take like the ImageNet model, which is trained, on as many as 10,000 classes, and we could take all of the output units of this thing. We could feed them through another layer, which was a NAM layer. So our final layer of this network could be a NAM layer, which is going to be interpretable. And now we could do things like we could say, oh, this object in this new class is like this because it's a 10% jellyfish, 20% starfish, a little bit of Katniss, and it doesn't look at all like a tractor or like a car. And what's really interesting about this is, remember, these are multimodal nonlinear functions, and we think that's really important for this sort of use of these as a basis set. And that's because if you look too much like a cat, you're probably a cat. So you only want to look a little bit like a cat. You probably, doesn't matter if you don't look at all like a cat or too much like a cat. It's sort of in the middle where something interesting is likely to happen. So maybe this is not something we've done, but maybe we could do something interpretable this way. And maybe we could even benefit from the fact that ImageNet has this hierarchy of images. Maybe this would help us create an even more nuanced explanation. So ultimately, anything that lets you create interpretable hidden units, interpretable activations, outputs of your model are fair game. For example, we could put these graphs at the output layer of a deep neural net, as I just suggested with ImageNet. But we can also, remember, this is just neural net stuff. We can embed this anywhere in the model we want. And as long as we're in fully connected layers, it's probably not going to hurt the model at all, because these are pretty powerful things. They're more powerful than a typical layer. So we can really embed these things anywhere we want. And then this means that parts of our model, those hidden units, will now be explainable as graphs. And to the extent that the things that are feeding into those nodes are interpretable, we'll be able to understand much better what this model is doing. So let me just wrap up. Hey, Glassbox learning and tabular data can be as accurate as black box learning now. It's not only very accurate, but it's fully interpretable, and it's even editable. We can fix those graphs when we see strange things. These neural additive models let us train multi-task GAMs, state-of-the-art interpretable deep neural nets. They're fully editable, they're differentiable, they do multitask learning really well. That's what let us do this personalized medicine that Ben did. And they scale nicely. They can be trained on GPUs. And we think there's many opportunities going forward to use these NAMs with deep neural nets, convolutional neural nets, and maybe reinforcement learning as well. In computer vision, we can apply these things on top of any interpretable basis function or model, such as we saw in Antonio's talk and Yixin's causal representations. And it's important to remember that we can use NAMs just for explanation if we want, but they actually are a learning method. NAMs are a part of a learning neural net. So you can use them also as part of your learning algorithm, and then that part of whatever they've learned will be interpretable. Hey, thank you very much.
Okay, thank you, Rich. We have time for a few questions.
And I think I stand between everyone and lunch, so.
Yeah. So I don't see anybody from the audience. So Dipti, is there anybody remotely that has questions?
Yes, there is a question. The fact that NAM performs comparatively to more complex models seems to suggest that feature interactions really aren't that important. To what extent is this dataset dependent? This is a question.
This is a wonderful question. There certainly are some data sets, especially synthetic ones, where third order, fourth order, fifth order interactions are important. However, there's a bias variance problem when learning from real data sets that maybe need some higher order interactions. And that is, there's order n main effects, there's order n squared pairwise effects, order n cubed three-way effects, order n fourth four-way effects. The hypothesis space grows dramatically as you go to higher order interactions. So it turns out you have a needle in the haystack problem of trying to learn which of the large number of three-way interactions is actually important. Not only that, then learning reliably the three-way interaction is also harder. Even if an oracle told you which three-way interactions were most important, just learning them from data is also much, much harder. So what we're finding is that, yes, these complex neural nets, deep boosted trees, random forests are more prone to learn three-way, four-way effects. Most of them turn out to be spurious, or they're learned so poorly that they actually hurt variance more than they improve the accuracy of the model. So by restricting ourselves to main effects and just a small number of the more learnable pairwise effects, it turns out we have a little higher bias than those complex models, but our variance is much lower. And it turns out it's usually a wash. That is, we actually end up learning something that's just as accurate overall because our variance has not gone through the roof by allowing ourselves to learn a too complex representation. I tell you, it is a shock to me. I never, ever expected that models that did no more than, say, pairwise interactions would be competitive on real data sets with models that are learning much more complex things. And now that we understand it better, we're able to see why. I do want to tell you the truth, though. Every now and then, 1 or 2 times out of 100, we do see a data set where, say, three-way interactions turn out to be useful. And our algorithms do generalize to three-way interactions. And in fact, often what we do when we detect a three-way interaction that's important is we quickly understand it. And then we try to create new features. We do feature engineering to push those things down into being main effects and pairwise interactions so that it's even easier for us to understand it. But it's actually remarkably rare in tabular data sets that you will benefit from three-way and higher interactions. Completely different story with pixels, of course. Pixels, I don't even like the word interaction when we talk about pixels, even though technically it is an interaction, a very complex interaction. Pixels, in images, we're learning something very, very different. It's a great, great question.
Okay, thank you. Dipti, are there more questions on the Zoom side?
Not at this point. Okay,
so I actually would have many questions, but I'm gonna pick one that kind of continues this discussion that you started. By the way, it's true. I've tried NAMs and different GAMs on tabular data set. It was very hard to find a data set where we needed the third order interactions. We found one, but I have a different question, which is you worked with all these data sets and with experts. So actually humans reading these explanations and benefiting from them. So now what I'm trying to get some feedback back from you is, how do human experts who are using these models, because you showed these graphs that are amazing at 1 order or 2nd order, they become heat maps, 3rd order, I'm pretty sure we can visualize them somehow, but I'm not sure how. So how do they, what do they say? Do they say, you know what, we cannot actually handle more than 2nd order interactions? How much interpretability gets sacrificed when we go to those higher orders?
It's a really good question. So the experts have no trouble at all with the main effects. It's amazing how quickly they pick them up. In fact, they often start understanding them better than I do. That's because they have the domain expertise. The pairwise effects, we have to help them a little bit with those in the beginning because they're a little more complicated. You have to reason about 2 features together to really understand what's going on. The three-way effects, the biggest problem is that they're now 4-dimensional objects. There's 3 features plus a response. So you have to present multiple views, or in certain cases where some of them are Boolean features, there are simplifications you can do, but they really do start to get more complicated. Sometimes we almost prefer to take 3-way effects and redescribe them almost as rule-like things. We try to present graphs that are almost rule-like in their interpretation for the experts. The experts surprisingly do not have too much trouble with this, and they pretty quickly don't need our help to interpret the models anymore, which is wonderful. By the way, half of the things we find turn out to be problems in the data that we didn't expect were there. It turns out pre-processing or data collection has screwed up, and there's just weird things in the data that we just never expected. And as a data scientist, I often ask the expert, any idea what that is? They have no idea what it is. And then I find it turns out to be a problem in the data. Half of the stuff we find is like that. Another half of the stuff is things that the experts are just sort of, oh, that's because we do the following. We don't admit people to the study who are over age 75 unless they have the following properties. So of course it suddenly looks like 75-year-olds are lower risk than 65-year-olds, even though that's not true, because the study requirement was such that you couldn't be in the study if you were over 75 unless your blood pressure and other things looked really good, because otherwise it would be a bad treatment for you. So, and then every now and then we run into something which is really just new science, and they're really amazed to see, oh, we had no idea that this kind of patient was this high risk. We really knew these other kind of patients were high risk, but not these kind of patients were high risk. So they really find some amazing things in these data sets. And they often want to make little corrections to the way the data is collected or to the model before they use it clinically, because some of the things they find really are sort of inappropriate. So, yeah.
Thank you.
Yeah, I think everybody should run and get lunch. So.
Okay, let's thank the speaker once again.
Thank you so much, Rich.
Hey, thank you. Happy to take any questions from anyone who wants to contact me privately. So,
thank you. I really enjoyed your talk, and yes, Rich is right. We are doing the a lunch break. I'm gonna share.
And I hope you guys want to use this in deep neural nets somehow that I haven't even imagined. And if you want help, we're happy to help. But I will go. Bye.
Yeah. We are working on it. Okay, so I'm gonna share the screen. So we meet back at 12:50 to start with the next spotlight session. I'm just gonna leave this open, and see you back soon. Yes. So let me just mute.